Hi, I'm Miss Boom. Today we're going to look at exponential models and applications. Now, what does exponential models look like? They are usually something that looks like that. So there's an amount which is equal to the original amount, A0, times b to the power of t, t often being the time. Now I can describe growth if b is greater than 1 or decay when b is less than 1. Growth examples are such as population growth, compound interest, or cell growth, things that grow. And decay are things like, for example, materials cooling down, where the temperature just plateaus, or radioactive decay. Cell growth equations might look something like this. We're not going to go into this today. Radioactive decay might look like this. We're going to do an example of this today. So an amount, the original, and now we have a K there next to the T, so it's slightly different. And the K is dependent on the type of material. Different materials have different K values. And during decay questions, we will see the word half-life. Half-life is the time it takes for half the material to decay. So how long it takes for half of it to be present. So every time you pass the half-life, the amount is halved. So example 1, a piece of paper that is 0.1 millimeter thick is repeatedly folded in half. Find a rule that gives a thickness. So this time we're going to do an exponential example using thickness. Find a rule that gives the thickness, t in millimeters, as a function of the number of folds. So you can see that the more you fold, the thicker it gets. So this is a growth example. Now you can do this by hand by doing a table. So how many folds you have. So if you have n is equal to 0, so no folds, we know that the piece of paper is 0.1 millimeter thick. But if you fold it once, then now you have 2 layers, so that's 0.2 millimeters thick. Now the 2 layers, if you fold it again, you're going to have 0.4 millimeters thickness because you have 4 layers. And if you fold it again, that's 0.8 and then 1.6. So every time you fold, you have double the layers. So every time you fold having double the layers, what numbers could you be thinking of? Well, 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8. So it looks like 2 to the power, but we also have to multiply by a decimal 0.1. So 2 to the n, so t is 2 to the n times 0.1. You could also do this by CAS. Let me take the CAS out and show you. So we're going to go to statistics, calc, regression, and AB exponential. So we're going to go to statistics, and I've plugged in the numbers, but you can put your X values in here, see 0, 1, 2, 3, and then your Y value. So when it's 0, we have 0.1 thickness. When we fold it once, we have 0.2 thickness, fold it again, 0.4, 0.8, and I stopped at 3 because we don't need that much. Now we can go to calc, then the word regression, where it calculates the best fitting line for us, and AB exponential, and you click on OK, and it gives us this equation here, A to the times B to the X, and A is 0.1 as we expected, same, and B is 2 as we expected. So you can use the CADs as well, any graphs, and then you can calculate x-intercept and whatnot with it using calc and solve. Okay, let me put that away. So you can do it by hand, working it out on the table, or using the CADs. But you see, you have to work out the Y values for this question anyway. I suggest you try both methods and make sure you're very familiar with the CADs. Part B, what is the thickness after 7 folds? So is that n or t equals 7? That is equal to n equals 7. So we plug into the equation 0.1 equals 2 to the n, so n is 7 now, and that works out to be 12.8. We can use the CADs and we can define our equation, so let's do that. You'll see that in year 11, you might not need so much to define your equation because you can drag and drop, but as you get into higher year levels, it's a good idea to define your equations because it will help you use the equation multiple times or combine it with another equation. So please do learn to use define. just gonna clear everything here first. So we go to main, action, and then command, which is down here. Then click on define, and now we do f of, and make sure you use this x over here, equals 0.1 times 2 to the x. Enter. So now we have to find x is 7, so that is f of 7. Enter. And that's 12.8. So that's pretty fast, as you can see. And if I had to find another value, I can just plug it into there really quickly. Okay, and then part C, how many folds are required for the thickness to reach 1 centimeter? What does 1 centimeter thickness mean? That means T is equal to 1 centimeters or 10 millimeters. Make sure the units are always the same. So plugging that into our equation, T is equal to 10. We have 0.1 to times 2 to the n. So dividing by 0.1, we get 100 equals 2 to the n. And we know what to do there. We log base 2, 100 equals n. Plug that into a calculator and we get 6.6. But it's asking how many folds. So we always have to round up, because if we fold 6, we haven't quite reached 1 centimeter yet. So the answer is 7 folds. We could also use the CAS calculator by using main, action, advance, solve. So I'll just quickly show you. So we go back to main, we go to action, advance, solve, and we this time we let f of x equal to, what did we want? 10. Enter. And we get 6.6. So again, the same answer as before, as expected. Example 2, and the last one for this video. Thanks for being so patient. After 1,000 years, a sample of radium-226, now don't worry about the 226, that's just the name of radium, has decayed to 64.7% of its original mass. Find its half-life. So what do we have here? We have a decay question. So the decay formula is that. Now we have T is 1,000 years. When T is 1,000 years, we have 64.7% left of the original. The original is A0. So at T equals 1,000, A equals A0 times 64.7%, which is 0.647. Now, if we plug that into the equation up here, so A is that, equals A0 to minus K, and T is 1,000, we can see that we can quickly cancel out the A0 on both sides. And now we can work out what K is by using log. So log base 2, 0.647 equals to the power, which is minus 1,000 K. I've just swapped them around. And then what do? Divide by negative 1,000. Plug it into the calculator, and you should try this on your CAS to make sure you get the same value. You should get 0.000628. Now we have K. Have we answered the question? Not quite. It says find its half-life. What is half-life? Half-life is when A is half of A0. So what is T when A is half of A0? How do we work that out? Well, just plug that in. So plug that into A. So half A0 into A. See? Now we work out what T is. So cancel out the A0s. Now we have that. What do? Log base 2, 0.5 equals the power minus KT. We know what K is, it's given there. But we also know how to write 0.5. 0.5 can be written as a half, which can be written as 2 to the power of, when you bring the 2 up over to the top, it becomes 2 to the negative 1. And then we know that one of the log rules is when you have a power, you can bring it to the front. So now it's just negative 1 times log 2. And log 2 is just 1. So now we divide by negative K on both sides. We get negative and negative, which is positive. So 1 over K, T is equal to 1,591.95 years. And always round up, sorry, not always, most of the times round up, depending on the question. Read it again. So the answer is the half-life of radium-226 is approximately 1,592 years. Thank you for watching, and try these questions again. See if you can do the same working out, and also use the CAS calculator.